Lecture 1, Color and Energy of Light. So in this lecture, we are going to think about the energy of light. And the energy of light is, of course, important because if the energy of light is going to match the energy level of the molecules, it can sometimes induce chemical reactions. So let's start from here. So first, what is light? So light is called as electromagnetic wave as another name, because as you see that the light, when the light is propagating, it means somehow oscillating electric field is moving like a wave. And at the same time, there's a magnetic field perpendicular to the electric field, and this one also oscillating. That's why light is called as electromagnetic wave, and they are propagating and perpendicular to the propagation direction, electric field and magnetic fields you can observe. And in many of the photochemical reactions, the key point is the light itself does not have so much varieties, meaning you cannot control many different types of light, because actually what you could control about light is only two parameters. And one is that this attenuation period, and this distance is called lambda, so wavelengths, or color. And the other parameters you could control is this. Amplitude is proportional to the intensity of the light. To be more accurately, the square of amplitude is equal to the intensity of light. So the thing is, if you want to decide the light, you only need to decide the color, meaning wavelengths, and amplitude. In various waves, light is kind of special because in the waves, only the light has the constant velocity for propagation. That's why, due to the relation between the frequency and velocity and the wavelengths, and also energy of light is related to the frequency. So once you decide the wavelengths, the frequency or energy is kind of determined. So that's why there are not so many parameters for the light. However, in many photochemical processes, there are so many varieties of reactions or interactions. This is not due to the light itself, but the materials or molecules have many more varieties. That's why the reaction has many varieties. So I want to keep in mind that light itself is quite simple in terms of the number of the parameters. Okay. So as a next step, as I mentioned, the light can be categorized with wavelengths. So you could categorize some of the light and then summarize some of the phenomena which each light can induce. Okay, so please please stop the video and then think about to fill in this chart. Okay. Okay, let's check a few answers. So at first, I will show you the wavelength region for ultraviolet, visible, and near infrared and infrared. And then depending on the textbook, the region of the wavelengths is a little bit different, but mostly it's kind of same, almost same. So in a way, so ultraviolet 200 to 380 and 400 to 700 nanometer. So depending on the intensity, and some of you can see, and also the sensitivity of your eyes, maybe you can see the more violet or near infrared region of the light. But it's one of the definitions. And then infrared is like 3,000 to 30,000. So it's order of micron in wavelength. And as you can see that the ultraviolet has a short wavelength, right? A short wavelength but a constant speed, meaning the very high oscillation. So in the case of UV light, it's kind of like a very high oscillation of electric field induced compared with for example, near infrared. It's kind of so you could somehow imagine that very high frequency oscillation can induce more higher energetic transition could be induced. So just here, briefly, I mentioned that as ultraviolet can induce electronic transition, even for like sigma bond, which is the basic chemical bond of and also pi bond. Some of the pi bond, high energy pi bond, could be excited. And in the visible light, similarly, some electronic transition could be induced, but most of the sigma bond is in the UV region, and some of the larger, for example, aromatic molecules, pi bond could be excited in the visible region. And in the region of the near infrared, mostly vibrational transition could be induced, meaning the molecules, right? So vibrational, in a sense, so molecules is connected with a spring, and it can oscillate the motion. This is a vibrational excitation. And in an infrared region, it's also not only vibrational transition, but also rotational transition can be induced. So in many cases, for the photochemical reactions, mostly these kind of electronic transitions are necessary because electrons are excited to induce the action. However, on the other hand, in the near infrared or infrared region, as you know that some of the heating device is using the near infrared or infrared radiation to heat you up by inducing some sort of the molecular vibration or rotational excitation, which finally gives you a heat, right? So, which is called photothermal excitation. Okay.